problem. Okay. This problem will involve different parts, so you kind of need to put all many different information together. Okay. So the first problem is about a spring. You compress a spring along an incline. Okay. So a block of mass with mass m equals to 10 kg is released from rest on a fractionless incline. The angle of the incline is 36.9 degrees. Below is the block. Below of the block, okay, is spring with K, the spring constant K equals to 4,000 Newton per meter. The block momentarily stops when compress the spring by 50 centimeters. So that's the maximum compressing distance. With this information, we want to find what is the speed of the block just as it touches the spring. Okay. So you have a inclined plane. (36.9 degrees). That is okay. And you have a spring here. And a block touches the spring with some velocity. Okay, that's the velocity we want to find out. How can we find it out? We know that along this inclined plane, the maximum compressing distance, and finally it stops here, okay, is 0.5 meter, right? 0.5 meter. That's maximum compressing distance. And the mass of the spring, we know the mass of the block is m equals to 10. And the spring constant K equals to 4,000. Okay? So we want to find out the initial velocity. And for this problem, which equation can be used to try to determine which equation will be the best one to solve this problem?
Spring potential energy.
Delta K equals W.
Yes. Okay, but you are talking about the mechanical energy conservation. Precisely, you should say delta K plus delta U equals to 0, or K naught plus U naught equals to K plus U. Okay. So here we can see that we mentioned this is a frictionless incline. So that kind of suggests us we should try to think about the mechanical energy conservation. Okay. Usually you can see if you have frictional force, you probably need to think about total energy conservation because you will destroy the mechanical energy conservation. Okay. But now we have frictionless incline. So you can think about this one. K naught plus U naught equals to K plus U. Okay. And once you identify the equation you're going to use, then you need to look at, this is our initial stage here, okay? We start to compress the spring. And this is our final base, okay? And in this problem, of course, you have the spring potential energy, right? You are compressing a spring. Do you have the gravitational potential energy? Yes, you have height change, right? Okay. So it's kind of similar to when you drop a block on the spring, right? You have both kind of potential energy change. So we need to further write it as K naught plus U G naught plus U S naught equals to K final plus U G final plus U S final. Okay. that's the equation you're going to use. Any question here? So the next thing is to identify the zero terms. Okay, of course you will have a lot of zero terms. So let's first think about kinetic energy. Is there any zero term for K?
The final.
Okay, how do you know the final kinetic energy equals to zero?
Because it's not moving.
This one stops.
Okay, it's momentary stops there, maximum compressing. Okay, here. And initial kinetic energy shouldn't be zero. In fact, it's related to the quantity we are going to calculate, V naught, right? How about spring potential energy?
Initial. Initial zero.
Yeah, initially.
Okay, initial zero because the initial state is when it starts to just before it's compressed. So it's in the relaxing stage, the spring. There is no spring potential energy. And finally it has some spring potential energy here. And how about the gravitational potential energy?
Final.
You can choose and make the final to zero, right? Okay, let's go to this extender. So this is our zero. So for our initial stage, we have some non-zero gravitational potential energy, right? It has some height. So final is zero. Okay?
Why did you make that zero? Why are you making that one zero?
Gravitational potential energy. You can always make one of them zero, right? By choosing that point as your zero height. So you don't have to choose the ground as your zero height. You can choose your final state as your zero height, right?
Okay, so that's our final state that we're choosing as our zero.
Yeah.
Okay.
Okay. When you talk about the gravitational potential energy, you have the initial position, final position. You always choose one of them as your zero position, right? Usually you choose the lower one. In this case, the final state is the lower one, right? Any question here? So now we have K naught plus UG naught equals to US final, okay? Now, but this problem you have to be pay attention to is that when you try to look at this height at this distance, so first, okay, let's write the general expression. Then you get the three remaining terms: 1/2 m v naught squared plus UG naught, so it should be mg y naught. Y naught is this distance. Okay, the initial height measured from our chosen 0 point equals to 1/2 k x squared. That's the distance. So let's check. We know the mass. We know k. Okay, that given number g, of course, a constant. Initial velocity is the quantity we want to find. So we need to figure out y naught and x. Okay, what's x? The comparison distance. 0.5. And what is y naught?
57.6.
Okay, y naught is not directly given, but we should have no problem to calculate y naught, right? So, can you give me the expression for y naught? Or maybe you can already get number. You already get number. 0.5 multiplied by sine 36.9 degree, which is 0.3. Okay? That's from the triangle here. So, it's like this. For this triangle, this is 36.9 degree, and this is 0.5 meter, the hypotenuse. So this height is hypotenuse multiplied by sine 36.9 degree, right? Okay, the geometry here. Do you have any question? So now, okay, you've got everything. So you get 1/2 multiplied by 10 multiplied by v naught squared plus 10 multiplied by 9.08 or 10.3 equals to 1/2 multiplied by 4,000 multiplied by 0.5. So you should be able to solve v naught Okay. In meter per second. Okay? So any question here? Okay, so for this problem, I think the tricky here is that the y naught is not directly given. You should be able to find it out from the geometry there. Okay? And also here, we have many terms, so you need to have a clear picture which term means what. Okay. Any question here?
The x value in the spring, the x value will be the maximum compression of the spring, right?
Yes.
Okay.
So that's your final stage. X is for that stage, what is the compressing or stretching distance measured from the relaxing stage?
And that's relevant in all cases.
It's always measured from the relaxed point. So it's relevant. Okay, but this usually will also just give that number. Like we say here, it's compressed for 50 centimeters. So of course that means it's compressed from the relaxed point. Okay?